So, hello everyone and welcome back again to the lecture series on air pollution, fundamentals of air pollution, sources, mitigation and its impact. If you just recall my previous lectures, in the previous lectures I discussed about measurement of carbonaceous species, and of course before that I have given a detailed lecture on the terminology that we use on the carbonaceous species. And in this lecture what I am going to do is really continuation on the measurement of carbonaceous species, organic and elemental carbon. I also discussed in the previous lectures that how to remove the carbonate carbon fraction that is associated with the mineral dust in aerosols. So those things we discussed in the lectures, but before we came into the final calculations, we were actually, because due to the lecture was finished and I have to continue the same from the previous one. So this is, I think we have discussed this from this one. So this portion, the first portion here, step 1 will give different fractions of organic carbon, and this will give actually different fractions of elemental carbon, and depending on the number of ramps that we are using, you will be getting different fractions of carbonaceous species. So usually we have OC1, OC2, OC3, OC4, these 4 peaks associated here. Then with the EC1 we have EC1, EC2 and EC3. This is 3 fractions that are associated with this one, and in between we have one pyrolyzed carbon that is actually part of organic carbon, but it comes under this peak. So we will now come to the measurement itself, that how it is being used. So just remember that these 4 fractions, and then the way organic carbon is defined, I just because I have written some equations, so I can just define here OC1 plus OC2 plus OC3 plus OC4, all the sum of all the fractions, and then there will be actually pyrolyzed carbon, because this carbon has been measured under EC1 peak. Okay, this will be measured under helium and oxygen atmosphere, so this will come here, but usually this pyrolyzed carbon is part of organic carbon, and therefore this can be written like this. And then we have EC. EC can be defined EC1 plus EC2 plus EC3 and minus pyrolyzed carbon, because you have to do subtraction of this one. Now you remember this, remember these equations. I have talked about this one is actually protocol that sunset ECOC analyzer used to have. There are and using this this analyzers uses National Institute of Occupational Health NIOS protocol. So just remember these things, that in the first step we get 4 organic carbon peaks, in the second during the inert and helium or helium oxidation heating, and then the other peak that we get actually in the elemental carbon when when switching the gas to the oxidizing medium, we get actually 4 peaks, and one peak that comes under oxidizing atmosphere, pyrolyzed carbon. It's actually part of elemental carbon or part of organic carbon, but it comes under elemental carbon, so we have to subtract this one. So let's go and see how it goes. So now you see here we have, this is the different temperature. So the very first start is actually first ramp temperature. So suppose you are this is actually, I told about lab is semi-continuous ECOC field analyzer. Here you remember that we start with room temperature. So the room temperature is usually set 25 degrees centigrade, or depends on the 25 to say let 45, or even let's say 5 degrees centigrade. So whatever the temperature is there, you have to see this one, and from this temperature, the first peak, it will be start heating and we will go up to 340 degrees centigrade. So in this one we will get OC1 peak. Okay, and the temperature hold time at 340 we will keep for 60 seconds, and then from here we will get OC2, then OC3, and then from this one we will get OC4. So 4 peak you get here, and then similarly you get EC peaks here. Okay, so for example, there are two, like two most common ECOC analyzer. One is Desert Research Institute and other is Sunset ECOC analyzer, Sunset Laboratory ECOC analyzer. So there are two thermo-optical or thermal optical carbon analyzer that are very common actually, based on DRI and Sunset. So DRI and Sunset are actually manufacturers, and there are different protocols. Most acceptable one is actually like then you have EUSCRI or something like that. I don't remember the name. So there are different protocols, but NIOSS protocol is one of the most, 5040 is one of the most accepted protocol. So sample is heated thermally in ramped steps in the presence of helium or helium and oxygen, and transmittance is continuously measured. This is very important. So the first thing will do, it will lead to evaporation of organic carbon and different fractions of this one, and this transmittance is continuously measured. This is usually used to define the split point between OC and EC. Okay, so just remember these things. And then how you define, because we are measuring the transmittance, so what will happen, the system has some initial transmittance, and this transmittance is actually because of the organic plus elemental carbon plus other aerosols that are there in the that are on the filter. So in the filters they are actually collected. So what will happen, we don't bother much about the other aerosols here, and because we don't have control, we are heating and we are using the properties of organic and elemental carbon. So for example, except dust, which is actually having a carbonate carbon, we don't bother much about other things. We will discuss this later. So the initial transmittance is basically because of this organic carbon, elemental carbon, and carbonate carbon. Okay, so this we will discuss this one how. So just remember. Okay, let's because we are discussing, so let's discuss what will happen. Initially at t is equals to 0, you have initial transmittance, say Ti, and as the t increases, as the time increases, what will happen to the transmittance? Can you guess? Because organic carbon is evaporated or removed from the system, Ti will increase or decrease? Ti will decrease, because the transmittance is now, sorry, transmittance will increase, sorry, yes, let me see this one, yeah, no, yeah, so initial transmittance, because you have whatever the organic carbon is there, that is removed, so it will be, the transmittance will decrease, and once the transmittance is decreasing, and what it do, when this all the organic fractions are removed, this pyrolyzed carbon will come, and this pyrolyzed carbon will give actually like kind of absorption, or it will try to absorb the radiation. So we will have more of absorption signal there, and because of this one. So initially if you talk about whether it is part of transmittance or absorbance, so initially the transmittance or absorbance, whatever you say, both the things, they will remain constant, and once the organic carbon fraction is removed, then transmittance will go down. Okay, and once the pyrolyzed carbon is coming, peaking actually, then because it is converted, because organic carbon is mostly scattering in nature, so it will not give transmittance signal. So most of the thing will be scattered, so you have actually transmittance, but when this comes, then it will be, you have different things that is happening here. And then what will happen when so split point is defined when the transmittance reaches to the original value. So when the transmittance reaches to T0, say initial or T0, whatever we are calling, so when it reaches to this one, this point will be called as split point, we will see in the thermogram. And then CO2 produced during each of the heating step is converted to methane. I told yesterday that this CO2 and plus H2, because we will be supplying hydrogen there, and you have nickel and you are heating this one, then CO2 and this will be converted to CH4. Once this CH4 is converted to CH4, what you can do, this one, this actually CH4 is measured using flame ionization detector. I also told yesterday there is actually another method that where the liberated CO2 that can be directly measured using NDIR detector. So there are two things actually. Initial measurements were mostly with the FID, but now they have come with the NDIR detectors, that is also used very frequently for measuring this one. So once you have done, you measure the signal of using FID, then in the last you known amount of methane is injected as an internal standard or external standard. So actually it is known amount of, this is I should put it actually internal standard, because this is used to convert the measurement. So external standard is when we put sucrose, so this is typo in this one. So known amount of methane is injected as an internal standard, and based on the signal and the conversion factor, you can get that how much CH4 is because of the organic carbon different fractions. Generally the precision and accuracy we talked about, we prefer to have less than 2.5% for total carbon and organic carbon, and for elemental carbon it is actually little bit higher. We will discuss more details of precision and accuracy in the coming lectures. So as you know, precision refers to the repeated measurements, agreement or kind of what degree of agreement between the repeated measurements, whereas accuracy refers to the how close we are to the true value. So basically, for example, you are running that standard and you are measuring that as a unknown sample. So you know that standard I have this much concentration, and you can then calculate this one. Generally these things, what the unit is given, actually it's actually relative percentage deviation. So you calculate that how much within the measurement. So you have like the difference in the measurement delta x upon x bar, you take average of those two and then you multiply by 100. So this will be actually like this much percentage. So we usually prefer to have these measurements less than 2.5% per total carbon. Remember these measurements are very robust actually, except that elemental carbon, this is most robust, but depending on the composition of aerosols, the accuracy and precision may vary actually, but we would prefer to have accuracy and precision less than 2.5% for TC and OC, whereas less than 5% for elemental carbon. Yeah. So now you see this peak. Okay. This is the sample oven and this is the filter punch that is actually kept here. This is a schematic of thermo-optical ECOC analyzer. Initial first step 1, only helium is coming, 100% helium is coming, and then this helium will be there, this filter punch is here, and we have it, because it is put in the sample oven, it will be heated, and you will see here this is actually laser that is giving this at 678 nanometer. So what is happening, this is continuously giving heating on this sample, and every time through the photodiode we are measuring how much actually in, so suppose I know this is I0 and then I transmittance, I know this one. So I will come to that one, that how transmittance and absorbance are related. So we will come to that one, but just remember now that it is keep on measuring absorbance or transmittance, and the point this is actually used to define the split point between EC and OC. So this filter punch will be there. There will be this helium gas will be coming and this will be going through this one. So whatever the carbon is evolved here, it will go in the form of carbon again, and then here it is heated. So this will convert all the carbon whether it is organic or elemental carbon, to CO2, and then this CO2 is converted actually to the CH4. Okay, we have a methonator here where this CO2 is converted to CH4, and then this CH4 is measured using flame ionization detector. This is a simple thing. In the second step, what we'll do, we switch this one, we close this loop now. In the first phase this loop was closed, in the second phase this loop is open and this loop is closed. So now we are not passing the helium, we are passing the helium and oxygen mixture, and then this will go, the process remains the same, and it will be actually, we will be doing the same measurement. So the kind of thermograph looks like this one. So you have, this is actually the red line is actually like the transmittance signal that is shown here, and then you see here that organic carbon and carbonate carbon will be here actually. This peak is usually carbonate carbon. Okay, so this and we have to integrate this one. Okay, we have to find out that how much carbonate carbon is there. This has to be removed, and especially in Indian aerosols we have lots of dust, so carbonate carbon can be significant amount. But before this one, you see here, this is the FID signals that we have here. So initially this is shown in the time. So you have in the time in minutes, usually it takes 12 to 15 minutes, and it takes about 3 to 5 minutes for cooling. So you have actually in 20 minutes almost like you can have one measurement, one sample is measured. So this you see at the ramp temperature heated, and this organic carbon is evolved, and then you see first peak OC1, then you have OC2, then you have OC3, then you have here OC4, sorry. And this is carbonate carbon, so it is not counted in the organic carbon peak. Now see, this is pyrolyzed carbon, or I wrote PYC, so you see the pyrolyzed carbon, and this is actually EC. It is not shown here, but EC also has 3 peaks. Okay, but all the peaks are not shown here. So you see here, this actually until this point you heated the sample up to 850 degrees centigrade, and that only in the oxygen helium atmosphere, so inert atmosphere. So there will be no evolution of this one. But when you have heated this one up to 850 degrees centigrade, and here you switch, temperature will reduce, and somewhere around this temperature will be reduced to 550 degrees centigrade, and then again stepwise heating we will do, and then 3 peaks of elemental carbon will come. The first will be for the pyrolyzed carbon, and here switch 2% helium gas that we are using here, and this from here. So before this split point, all the things will be like organic carbon and carbonate carbon. From here, whatever the evolution comes will be called as EC. So because the integration in such a way that pyrolyzed carbon is actually calculated, because you see here pyrolyzed carbon has come into the oxidizing atmosphere, 2% oxygen plus helium. So pyrolyzed carbon has come here. So this will be actually, if you don't correct, it will be actually wrongly given as a signal of EC. And this is what is the initial transmittance. So you see the transmittance keeps on continuously constant, not changing much, but at the high temperature when this pyrolyzed carbon is formed, the transmittance decreases. Okay, the organic carbon is converted to the pyrolyzed carbon, and then when you switch this one, this pyrolyzed carbon is again heated, and then once it gets oxidizing atmosphere, it is converted to CO2, and then we measure this one. So there is a sharp peak here, and then this will be actually increase, and then when the transmittance reaches to this one, then it will be defined as a split point. So just remember the terminology. This is little bit complicated, but when you read couple of times you will be able to understand this. This is actual thermogram that you see here. You see initial transmittance, that line is here, and then it's somewhere here actually you can see the split point, because you have to remember, you can say that okay, initial transmittance somewhere here it could be equivalent, but you have to remember that it has to be between oxygen and helium environment. So you can see here EC1, EC2 and a very small EC3 peak, and then this is actually PYC or pyrolyzed carbon. So this you have to remember, and then the other peaks like OC1, OC2, OC3, then you have this is carbonate carbon, by the way, and then little bit small peak here will be, or here actually this will be actually like OC4. So 4 carbon will be there and the data that you will get, it will be given like organic carbon 23.52 for example here, and then uncertainty is calculated like 5% generally of the measured signal. There is no standard way of doing this one, so they usually take 5%. Initially you see this carbonate carbon is 0 because it has not measured. So the system has kind of very good software. So it says that when the integrate between, say, usually it comes under 220 to 280 seconds. Okay, this carbonate carbon will come if you use ECOC analyzer, and during this peak you just calculate this one. So if when in the program you see here manual peak started, so you have actually like here you put 220 and then you put 280. Okay, so between 220 and 280 the carbonate carbon will come. So once you have calculated this peak will show carbonate carbon, and then organic and elemental carbon will reduce, and then you have a total carbon and then uncertainty that is associated with this one. Okay, similar thing is shown chairing one. I talked about optical correction, that we have actually like optical corrections or chairing, or this is also called chairing, or this is called pyrolysis. Both the things it is called, so it depends on what terminology you are going to use. So pyrolysis, chairing and many things. So you see here this peak is actually like from here to here, this is actually a pyrolyzed carbon. So this is very important and we must remember these things. You see very nice peak here, initial absorbance transmittance decreasing, then it start decreasing, and then it's somewhere it start peaking here, and then you see here then goes like this, and then transmittance, like initial transmittance equals to here. So this is actually like between this 2% oxygen plus helium atmosphere from here to here. So you can remember this peak because it is coming in this one, so this is pyrolyzed carbon. Prior to this is actually what you call organic carbon. So this is the point that you have to remember. This is very important. Otherwise, if you don't do the calculation, and then you see very clearly this calibration peak, which is actually using as a methane. So you can see the differences, and then we have 4 fractions. So OC will be given by sum of OCI. OCI is running from 1 to 4, and plus pyrolyzed carbon, where EC will be given as ECI, sum of these things I is running from 1 to 3, and then you have to subtract from here. So just remember these 2 things when you are finally doing the calculation. By the way, the software gives, for example here in this one, the software directly gives the numbers to you, total organic carbon. It doesn't give the different fractions, but if you look at the text file, result text file, it will have all the different fractions. Okay, so you have to it will have different fraction of carbon. So, and then you will also notice there that actually this initial transmittance value is also calculated. Then you will also find some value like attenuation. We will discuss this one in next lecture. That is also given. So from this attenuation you will be able to calculate absorption coefficient, generally written as BS, absorption. Okay, yeah. So I think I made it clear that how different fractions, how thermo-optical ECOC analyzer is used, and how we can, how beautifully you can use these equations to calculate what you call all different fractions of OC and EC, and then using the initial transmittance and when it keep on changing. You can also see the pyrolyzed carbon that is happening, produced during the reactions, and you can calculate all those fractions. So this is really very important and very good instruments to use this one. The point that is important here, because we are measuring the transmittance here, so this transmittance can be converted it actually into absorbance, okay, and this absorbance is usually written as attenuation. In the equations we will see, and this attenuation, because I know that how much area I have used, I know that, for example, how much area of filters I have used, centimeter square, and then the volume is actually in meter cube. I can calculate what is the value of B absorbance from here. And not only that, because this instrument is also giving me EC concentration, so I can calculate mass absorption efficiency, which is actually B absorbance by EC. So we will see some of the calculations in the coming slides. So B absorbance is actually reported million mega inverse. 1 mm inverse is equals to 10 to the power minus 6 meter inverse, and then we have EC concentration like reported microgram per cubic meter. So from this one you can see that MAE unit will be actually like meter square per gram. So we can calculate, we will do some calculations there. So I think I have been able to give some insights of thermo-optical ECOC analyzer. It's a little bit complicated. Measurement is although very slow, very good. It doesn't involve much of the complications, but you have to understand that how to do the carbonate corrections and how to involve these things. Because just one more things I talked about. This was actually this peak I talked about, carbonate carbon. This one. So here what you do, you once do unacidified samples. So this means it will have Cc plus, okay, and when you do the samples, you acidify this one, what will happen? You have removed carbonate carbon, okay. So if you see when you run this acidified samples, this carbonate carbon peak you will not see. And I told that if you can just locate that what time it is coming. So usually it comes like 220 to 280 seconds. So since it is coming, Cc peak is coming at this time, you can manually integrate. I have shown this one. And when you manually integrate, you can give carbonate carbon, and then you can correct that one. Carbonate carbon usually will be given in the form of OC, so it will be subtracted from organic carbon. Okay, so I hope that I have been able to give some insights of thermo-optical ECOC analyzer, and in the next lecture, before we use optical measurements using black carbon measurements using optical methods, there is actually like different terminology like transmittance and then reflectance and then the Beer-Lambert's law is used. So I will discuss first the Beer-Lambert's law and then come back to the optical measurements of black carbon. So till then, take care and bye bye.